So, okay, so let me go back to this slide just for a second, for a few seconds actually. So I would like to discuss just a few very simple physical examples when we think we have an answer even before we solve equations, before we look at the equations and try to understand what this physical system wants to do. Okay, so basically, again, in these few examples, which I would like to discuss before moving to other stuff, so our basic equation is either this one or this one. So the only difference between them, this one is non-dimensional and this one is a dimensional one. Sometimes, I mean, for some physical intuition, it's better to look at the dimensional version, but it really doesn't matter. Okay, so we saw this. So the first example, just to remind you what we did in the last few minutes of, I think it was yesterday talk. So we looked at a case where the wind is blowing along the surface, and we try to understand what happens with the film. Okay, so let's move to a different example. So now let's look at the second example. Now the second example is shown here. No slip, okay, no external forcing. Pi, this is a normal component of the external forcing imposed. Okay, so pi is 0. At tau, it's also a wind. A shear stress is also 0. Now there is no wind. Okay, and surface tension is a constant. So there is no stress just coming from variation of the surface tension along the surface. And there is no body force. Actually, there is a body force. But the body force is a conservative body force, it's just gravity. Okay, so I incorporated it into this sort of generalized pressure, so it appears here. Okay, G is G. Okay, so when we go back to this equation, we substitute it here. A tau 0 is 0, that's a wind. Sigma is a constant, so this one does not appear. Beta is 0, and P, this generalized pressure, it has a gravity component in. So basically, when we plug it in, everything into that equation, that's what we find, this equation. And this equation is in physical variables, which is the dimensional one. Okay, so we see a viscosity here. We see the action of gravity here, G. And we have surface tension. So the surface tension term looks exactly like in the previous example, because there is no change with respect to that. Okay, so now, and now again, and this version is a dimensionless version of the same equation. Okay, so basically what we see here, let's look first at this dimensionless version of the equation. G, it's called Galileo number, and the Galileo number is defined here. So G, okay, the capital G, the Galileo number is just the ratio between the gravity effects and the dynamical effect, which are shown here. U0, by the way, we have not picked up yet the typical velocity, U0, so it stands here as is, but in most of cases, when we don't have anything special, yeah, here. U0, okay, maybe it's chosen in the following way, as nu divided by H0, where nu is the kinematic viscosity of the liquid, of the fluid. Okay, nu, the units is meters squared per second, and okay, H, of course, that's the mean thickness of the film, that's a meter. So if you plug it in here, so you have units of velocity, and this is a typical what's called viscous velocity in the film or in the fluid system. Okay, so but basically here we don't need to specify this U0, but if we need to make a decision, so this is definitely one of good candidates for that. Okay, now, okay, so this is the Galileo number, and by the way, if you choose this a velocity, a typical velocity. So then G will be rho G H0 cubed divided by nu squared, because mu is actually rho in u. Okay, rho is a density, and nu is a kinematic viscosity of the fluid, and mu is a dynamical viscosity of the fluid. Okay, so basically you have this if you pick this choice. Okay, now another guy is the guy you know from yesterday, or maybe even before. That's the inverse capillary number, okay, which measures the relative importance of capillarity effects and dynamical effects in the system. Okay, so now this is the equation we want to look at. And even before we try to look at stability, by the way, of course, okay, any constant, okay, for H definitely satisfies this equation, because if it's a constant, the time derivative is 0, the spatial derivative is 0, so everything 0 plus 0, no, 0 minus 0 plus 0, it's still 0, okay? So it satisfies the equation. So before doing this kind of linear stability analysis like we did it yesterday, so let's try to project what kind of physics we expect for, okay? So basically what we have here is the following. Okay, we have a table and we have a film. Okay, on the table, gravity is, of course, is acting in this direction, okay? And we have surface tension. Now, let me ask you a question, students, please. Okay, so we have a film. Okay, we disturb a little bit the flat, okay, otherwise flat interface. Okay, what would you expect physically to happen? Okay, on the table. Okay, we pour water here. Well, it's not allowed, but let's do it. Okay, so would you expect some evolution for this surface, for the interface of the fluid? Or maybe it will just relax after some time and will become flat? Or what do you think? Yeah, that's okay. That's why I asked. Okay, of course, I mean, I would expect that a gravity will bring down any kind of disturbance, and surface tension, which wants to minimize the surface energy. In this case, it will try to minimize the surface area. Of course, everything would like to be quiet. Okay, that's what we think on physical grounds. Now, can we see it from the equation itself? And the answer is yes. Because, okay, let me move these guys to the other side of the equation. Let me assume for the moment, yesterday I said that if you discard a capillarity, then it's a catastrophic effect. Not yet, not in this case. Okay, so if we discard this one, if we assume arbitrarily that C bar minus 1 is 0, okay, so then what do we have here? So this does not exist there. This guy sits on the right-hand side of the equation. So what would you expect to have? Okay, this equation is what? Is nonlinear heat equation, right? Where the heat, the thermal conductivity, so to speak, is proportional to h cubed. Let me write it here. Okay, this is a heat equation, right? A linear heat equation, right? Or I can write it something like this. Let me write it alpha here, h, okay, x and x. Actually, I don't need this. Okay, that's a linear heat equation. If I have a disturbance of a flat state, okay, what happens? It smears out and it becomes, well, given the certain boundary conditions, of course, it will smear out and will become flat. Now, this equation with here. Okay, with this guy 0, so we have ht equals, say, g over 3, a constant, h cubed times hx and x. That's exactly what we have, okay? So basically this guy, instead of alpha, that's a thermal conductivity, so to speak. So this is nonlinear with respect to h, nonlinear thermal conductivity. That's a nonlinear heat equation. And by the way, okay, how about the sign? The sign here is a positive, because G is a positive. Well, A3 is also sometimes a positive. And H, physical thickness of the film, okay? It's also a positive, or in the worst case, it's 0 when it ruptures, okay? But it shouldn't be negative. So that's why this is sort of nonlinear heat equation. So if I have a disturbance, and if the boundary condition allow me, so the disturbance will die out, and everything will become flat at the end of the day, okay? And I should say that this, if you bring it to the other side of the equation, it acts absolutely the same way, even faster in a way, okay, than the heat diffusion, okay? That's sort of super diffusion. It will act even faster. So both on the physical grounds and on mathematical grounds, we expect that any disturbance will die out. Okay, so let's see what we can see from the analysis. Okay, so let's assume, okay, so we find this a constant solution to be a solution of the equation. Let's make linear stability analysis. Again, we do the same as yesterday. Let me remind you. That's exactly what we said. Okay, let's assume that there is a disturbance. Okay, S is a growth rate, a complex growth rate. K is a wave number. And H0 is much smaller than H0. Okay, let's substitute it into that equation, and we'll find the following. That's what we find: the dispersion relation, which is the relation between the growth rate and the wave number of the disturbance. This time looks like this. Okay, so which means, by the way, how about its nature? Is it a complex, or it's always real? It's real. Okay, you know, but okay, it's always real, which means, okay, what does this mean? Okay, the real number for the growth rate means that there is no complex part or imaginary part for the growth rate, and the imaginary part brought into life, actually yesterday, okay, a propagation of a wave. So and in that case, in that example we discussed yesterday, the propagation was due to the wind. So the wind induced sort of wave propagation. Now there is no wind, so there is no propagation. There is no propagation. The growth rate is real, which means it can be either positive or negative or 0. Okay, so let's look what happens to this guy. Okay, S, that's the growth rate. Mu is just a factor. Okay, how about the sign of this? Oh, it goes by diffusion. It's so slow. What? It's negative. It's negative. Nothing to do about this. 1 is E positive, 3 is E positive, H0 E positive, and this guy E positive. Or maybe 0 if it's infinitely long disturbance. And everything here is E positive, and nothing to think about, okay? So what does this mean? It decays. Okay, the growth rate is negative. This exponential, which we had here, is okay, this is negative, so it means it decays with time. That's exactly what we expected even before looking at the equation, okay? Both on the physical ground and mathematical ground, just by staring at the equation and projecting what this equation wants it to tell us. That's one of the things it wants it to tell us. It will decay. The disturbance will decay, so the system, this physical system, prefers it to stay in a flat state. Well, not really exciting, not really surprising, but that's life. Okay, good. Okay, so, okay, here I wrote, okay, S. Okay, S is real, okay, and negative, so it means stability. And of course, it's just a film leveling. You put a pile on it, you brought water here, it decays. It wants a gravity, it drives it back surface tension reduces the surface area. And that's it. That's the end of the story. Okay, I don't need to press over there. Okay, so now I would like to look at the same equation a little bit differently. And this approach definitely is very important, not only for this, but for some other examples. One of them we'll look at, and at many examples we will not look at least not now, not during my current visit. But it's also possible to use this technique. Okay, so we are talking about this equation. Okay, what I want to do is the following. I want to write, or actually to rewrite my equation in this form. Now let me explain what you see here. df, a delta f by delta h, this is a variational derivative of some f, which I don't know yet what is this, with respect to h. Okay, h, this is a dimensionless thickness of the film. And this is dx, so okay, x derivative of the result of this variational derivative. And h cubed is some function, which is h cubed. Normally it's called a mobility function for some reason. I will not discuss this. And there is delta dx outside of the whole business. Okay, so let me guess, okay, that, okay, this guy, okay, f will look something like this, okay? I don't know why, but, okay, I chose it this way. Okay, so let's see. Okay, let's calculate step by step what we wanted to see. And compare the result of what I wrote, okay, it compares the result to our original equation. Okay, so del f delta h, okay, so it looks like this. Okay, okay, f is integral. And by the way, I will impose periodic boundary conditions just to make sure all the terms after integration by parts will vanish. Okay, so, okay, okay, this guy L be the size of the periodic domain. And this f is, say, f some function which it depends on the function itself and the first derivative and integrated over x, okay? So del f del h is actually df by dh minus ddx of df by dhx, right? This is a variational derivative of this functional. Okay, so if I use this expression, so df dh, that's exactly g 2h divided by 6, that's exactly what I got, okay? This part, now I need to differentiate this f, this function with respect to hx, okay? 2 times c minus 1 hx, and then I differentiate it once again, so that's what I get. Okay, e2 divided by 6 is 1/3. That's what I get, okay, this. Now I need to differentiate once again, so that's what I get. Now I need to multiply by h cubed, that's what I get. And now I have to combine all of this, I have to differentiate once again, that's what I get. Okay? Now let's see if there is any difference between that equation and this equation. That's exactly the same. Okay? So I found, okay, f, which is, I will not like to reveal its identity at this moment, maybe in a few moments from now, but I found some f, which looks like this, which actually helps me to rewrite or to recast my equation in this variational form. Okay, now you may ask, why do you need all of this? Well, I don't know yet. Maybe in the next slide, it will explain me and you why. Okay, so let's see. So I know that my equation, okay, this equation, I can rewrite it in this form with this f. Okay, now, okay, so again, this is the equation, this is this guy f. Okay, now I would like to ask myself what happens with this guy f with with respect to time, which means as the evolution of the film, I impose some disturbance at t equals 0, for example. I want to know what happens next, what happens in 5,000 years from now, okay? So I would like to know, to understand what happens with this functional f along any trajectory starting from the initial disturbance. What happens, how this f, by the way, f is a scalar quantity, right? After integration, so I have a number, okay? But this number depends on actually time. Why? Because this guy, okay, h depends on both time and space, right? After a spatial integration, so I have a function of time, and I want to know how it responds, how it behaves with time. Okay, so let me calculate df by dt, okay? That's exercise in differentiation. Okay, so df by dt, so it's 1/6 of d by dt of the whole thing, okay, equals, now I differentiate this. Well, of course, let me assume that all, what's the name of this theorem, a Fubini theorem in math, right, that you can interchange limits, because now we have two different limiting processes. We have integration and we have differentiation. So the question is whether I can interchange them. Let's assume we can, or we may. Okay, so so I bring this guy, the differentiation, inside and differentiate with respect to time. Okay, so out of this h squared, I get a 2 times h sub t. That what I get from here. From here, I get similar thing. And the integration with x. Now let me integrate this guy by integration by parts. This one is left as is. Okay, so integration by parts. So I integrate by parts. I don't need to explain how to do this. And again, I impose periodic boundary conditions. So the terms after integration by parts, they are 0. They vanish. They just cancel each other. Okay, so this is the integration by parts. Now I combine these two terms, 1/3 gh minus 1/3 of this times the second derivative, all multiplied by ht. Okay, equals to this. Okay, again, integration by parts. Okay, integration by parts, no, sorry, it's not integration by parts. Now I use my equation. Now I substitute this equation here, okay, instead of this time derivative, and that's what I get. This is my equation, actually rewritten in this form. Okay, and now again I use integration by parts. Okay, sorry for the complications due to integration by parts, but it turns out it to be a very powerful thing. And finally I get this. Okay, so when we look at this value, what can we say about its sign? Okay, h is positive always, or 0 at most. Okay, how about this one? It's a square of something. So it's at most 0, but normally positive. So the whole thing is negative. Negative along any trajectory starting from any initial condition. Okay, so which means that df by dt is negative or 0. So which means if I start with something which even I don't know what, okay, as an initial disturbance, so along the trajectory, which might be complicated, I don't know it before I numerically solve the equation. But even without the solution, without using, numerics, so I can already predict, or alternatively, I can solve numerically my evolution equation. And this inequality, okay, may be used for a control or for accuracy checking of your numerics. You check while solving your solution from one time to another time, you must check that this value decreased. Okay, otherwise something is wrong with your numerics. Okay, so you can use all this insight even there. Okay, so basically what we find, the df by dt is negative or 0, which means this value decreases with time. Okay? Now, if we look at the value of this integral, one more thing can be said without saying, okay? This guy is larger or equal to 0, because everything inside is a positive or 0, right? So now I found something, some value, okay, f, and this value decreases along any trajectory, and it's bounded from below. So that's why now I can reveal its identity. It can be called either a Lyapunov functional for this system, or it can be called a free energy of this system. Okay? Now, okay, if, going back to math, if we have a functional or a value, a function, it doesn't need to be a functional, which decreases with time, it satisfies a certain differential equation, and it's bounded from below. What can be said? By one of the theorems, definitely you learned at some stage of your education, maybe not in the kindergarten, but okay, right after that. Okay, so there should be a steady solution for this. There should be a fixed point of this differential equation. So there should be a steady state of this system. Now, going back to our physical analysis before we looked at that, and going back, looking again at our mathematical analysis we performed, we know that if we have a physical system, if we do this experiment here on this desk, okay, we disturb the film, it wants to relax, it wants to be leveled and to go back to the original configuration, right? This is exactly the steady state, which is predicted by the existence of the fixed point for this Lyapunov functional. Okay. So that's exactly what I said. Okay. Okay. So what is the state? Because of the final state is just a flat state, and because of our scaling of for h. Okay, h was the physical thickness of the film. We scaled it with the mean thickness of the film, right? So the final destination is just h equal 1. That's the location of the mean thickness of the film. Okay, so this example was sufficiently simple from both the physical intuition and mathematical intuition we developed, so we can sort of sense what's going to happen even before going to the computer and solving that evolution equation. But if you solve it, I will not discuss numerical issues unless you ask. But okay, so basically if you solve numerically that equation, which equation? Yeah, this equation. Okay, so you start with any initial condition. If you use periodic boundary conditions, it decays. Finally, at long time, you find the solution is flat, exactly h equal 1, with some numerical noise, of course. But if you run it more and more and more, even the level of this numerical noise decreases. Okay, so, okay, any questions, by the way? If you have questions, please, even many questions, you can stop me and ask. Don't hesitate to do this. Okay. When you talk about a wave, a propagating wave? No, it will not propagate here. Because think about the experiment. Okay, think about a bath I have here. Think about liquid here, liquid layer, so I do something. Okay, wash my hand there. If I don't do something like this, if I don't push the system in one of the directions along the x-axis, so what would be the reason to move either left or right? There is no reason. Actually, look at the equation. Okay, look at this equation, for example. Okay, if you substitute, okay, x instead of x, if you write minus x, you just say, okay, x is not going this direction, it goes in this direction. What will change in this equation? And nothing, because if you change the direction of x, so okay, every derivative will get -1, right? But how many -1s you have here? 2. So nothing will change. Okay, so if you don't do something okay on purpose, nothing will happen. Nothing will lose symmetry, okay, left-right symmetry in this case. Okay. Yes, yes, but exactly, but for this you have to do something. If you don't do something, so it will decay just staying in one location. Look here. Yeah, here.
Maybe the main problem is that you are not discussing gravity waves at all.
No. Yeah, there is no gravity waves.
They decay very fast, so they decay on another time scale, so they don't appear in this analysis. They already decay.
Oh, I see. That's what you meant. Okay, a gravity capillary waves. Okay. No, it's different. It's a different case here. Yeah. Well, actually, yes. Of course, if you have a gravity wave, definitely they will decay. But again, I mean, standing wave, it will be a combination only. I mean, it's such a combination of the waves because not to break the symmetry, and the symmetry will allow only for standing waves, and they will decay. Sure. Just because of viscosity. Actually, even gravity waves, when you have a viscosity, I mean, actually, I think, yeah, for sure. For small viscosity, you can actually, work it out analytically. So there is a decay, something like exponential of -12 nu t or something like this, or nu squared even. No, nu t. Nu t divided by something, just to cancel these units. But it eventually decays. Okay. Good. Okay, let's go to a little different case, but it's still of the same family. Now I would like to look at the case of negative gravity. Okay, negative gravity, well, you might say, where last time you saw negative gravity, yes, I never saw it, but if you put your liquid, your bath, okay, not here, but on the ceiling, that's exactly the case of a negative gravity, okay? Okay, and this brings me to the term which is well known in the scientific community, and it's called Rayleigh-Taylor instability. Okay, now, okay, let's think about this physically. Okay, you put water on the ceiling. Well, basically, it's actually possible, right? Because, well, we never saw it for some reason, but basically, I don't see any contradiction. Okay, imagine here is your ceiling. Okay, here is G, right? And here you put, okay, water, okay, H0, that's the main thickness of the film. Okay? Now, okay, I claim the following. This guy can live, okay, happily on the ceiling. Okay, if the pressure, okay, exerted by, the atmospheric pressure from below, it will equilibrate or be more than the weight of this guy, right? So if I calculate the weight, how much is the weight? The weight is, let's assume that this is, I don't know. Okay, this is A. Okay, so how much is the weight? Is, okay, rho G times the volume, right? How about the volume? A squared H0, right? Now, how about the force? The pressure, a force exerted from below. How much is that? It's PA, that's atmospheric pressure. Let's assume that it's a constant, times the area. How much the area? Okay, A squared, right? So I want to W to be, sorry for that, to be smaller or equal to P, just to allow this guy to live happily on the ceiling, okay, rho G times A squared times H0 should be less or equal to PA times A squared. Well, A squared, it cancels. So H0 should be less or equal than PA divided by rho G. Okay? So let's make a hardcore a computation here to find how much H0 should be. Okay, so H0 should be smaller or equal to PA divided by rho G. How much is PA? 1 atmosphere, how much is that? It's 10 to the 5th bar. Bar is what? Is Newton over meter squared, right? Something like this. Okay, rho, let's take water. How much is rho for water? 10 to the 3rd kilogram over meter cubed, right? Times G. How much G? Let's assume with 10. A discount, okay? Meter over second square. Okay, so let's see. This and this and this go away. Newton is how much? Newton is a kilogram meter per second square. Okay, something is missing here. No, it's okay. Okay, so this goes with this, and we are left with meter. Okay, how much is it? 10 meter, right? Okay, 10 meters. So just to attach a liquid layer just to the ceiling, well, you should not exceed 10 meters. So if you want to put water on the ceiling for up to 10 meters, 7 meters, if you want 8, you can do it, and it will stick there. Okay, when last time did you see it? Well, I don't recall when I saw it, but possible, apparently, right? Based on these static considerations, right? But I'm sure that everyone sitting here will thinks, well, why not? I'm not sure why not. Okay, well, in any case, let's think differently. Let's leave this riddle aside. I will come back later to it, to the resolution of this paradox. But, I mean, you can check the calculations. They are absolutely correct. Anyway, okay, so now this is a sketch. This guy did not like the 10-meter layer. Did not survive it. Something is wrong with it. Huh? It's my fault, sorry. Okay, I switched it off. Okay. So this is a configuration of the system I'm talking about now. Okay, so this is the substrate, this is the ceiling, this is the film, this is G direction. Okay, so now there might be some disturbance on the surface, and I want to know what happens next. That's my intention. Okay, the evolution equation. The evolution equation, I don't need to derive it once again because I have it already. I had it in the previous example. The only difference is the gravity is negative now, so to speak, right? So this is the equation. In the previous case, in the positive gravity case, this guy with a negative sign. Now it's with a positive sign. Okay, now let's look at the equation, and this is its a dimensionless version. So now let's look at this equation. Let's make this, by the way, what happens on the physical grounds? What would we expect apart of this? Will this guy of 7 meters thick, will it remain there, or it will do something else? I need suggestions. Guesses? No guesses? Okay, let me ask again. Okay, will it remain there? No. Well, we can bring someone just to fix 7 meters above us, so we look at it, whether it will remain there. Okay, so I think nobody believes that it will stay there. So what happens, okay, if it doesn't stay there in this configuration, okay, what happens? Okay, there is rain, right? It may be heavy rain just falling like this, or maybe doing something else, right? That's what I would like to know, to see from, not from my gut feeling, but from maybe from the solution of the equation. Okay, so, but before that, let's look at the mathematical object which is shown here. Let's try to predict what happens here. Okay, so this case is a little more complicated than the previous one, as you guess, right? Basically, we can perform well, even before doing this linear stability analysis, let's look again at this equation. And now let's assume that C bar minus 1 is 0. So we neglected now the capillarity, and we are left with a much simpler equation, by the way. We are left with this guy, minus G over 3. It's only this one, right? H cubed HXX. So we have only this. Okay, so what can we say about this guy? It looks like what? Does it look like a heat equation? A nonlinear heat equation? Yeah, it does look like a heat equation, but with a negative sign. So the sign is sort of wrong. From the mathematical point of view, this equation is a diffusion equation, but because of the sign, it's called backward diffusion. So which means if in the heat transfer course, you were taught to solve the problem, okay, here is the rod, okay, here is the initial temperature distribution, okay, what happens in 5,000 years from now? What is the temperature distribution in that rod? So you could calculate it, right? But this sign, okay, asks a different question. Okay, here's your rod, okay, here is the current temperature distribution. What was the temperature distribution 5,000 years ago or 10,000 years ago? Now the question is, and this is a real question, okay, is it possible to solve this problem? And the answer is no. There is no way to know, okay, even after maybe 3 advanced courses in heat transfer, it's impossible to know what was the temperature distribution 5,000 years ago. Not 5,000 years ago, 5 seconds ago. It's okay, it posed mathematical problem. It's impossible to solve. Okay? It's impossible to solve. There are some reasons. I don't want to discuss them, but there are some simple arguments why not. Okay? So this is nonlinear heat equation, but backward diffusion equation. Okay? But so we say that if you try to solve this equation, so the solution blows up in finite time, which means the solution becomes infinite somewhere, not everywhere, somewhere at a finite time, which means actually the thickness of the film, if we talk about this, the thickness of the film somewhere becomes infinite. Okay, when's the last time you saw a film starting from this and going to infinity? You didn't see it, I never saw it, nobody saw it. But this is a hint that something wrong is going on here in the physical system described by this equation. If you discard this term, if you say there is no capillarity, I don't like this capillarity, it brings, okay, higher derivative, I don't like it. Okay, so this is a catastrophic effect, which I spoke about yesterday. You cannot dismiss a capillarity when you have a system like this. Okay, you must keep it by force, because otherwise it brings you, the whole thing brings you to the equation which is mathematically ill-posed. it's impossible to treat. So you have to have capillarity. The capillarity here is it's the only sort of only mechanism keeping you from a catastrophic effect like this. Okay, but this tendency to increase the amplitude of the equation somewhere in the domain, it hints actually the physics of the system. The system, as we understand, will not remain like this, 7 meters thick, even 1 centimeter thick. It will not survive as is. Okay, because there are some mechanisms which are not governed only by statics, considerations. Okay, there are some other things, dynamical effect, which you must satisfy. Okay, now how about dynamics? Let's look again at this equation. Let's perform linear stability analysis. So again, you substitute the guy, well, similar to what we already did many times. More than one is many. Okay, and that we get this dispersion relation. We have the relation between the growth rate and the wave number of the disturbance. Okay, looking at this again, how about it? Is it the growth rate? Is it a complex or real? It's real, right? It's real. Okay, how about its sign? Oh, now it's more complicated. Okay, now it's more complicated because this guy, no, not this guy. Okay, this guy is always a positive, but this one, well, it's negative. So there is a competition between the two factors here. Okay, there is a competition between gravity. That's why, by the way, that's why it's advantages or beneficial in some sense to look not only at dimensionless equation, but at the dimensional equation, because now you have all the ingredients shown explicitly there. Okay, so you look at this guy comes from gravity, and the gravity is negative, remember. This one is coming from capillarity only. So there is a competition between the two. Okay, now whatever wins, wins. Okay, but what we can see for sure is the following. If k is sufficiently small, what does this mean? K is small. The wave number is sufficiently small, which means the wavelength is sufficiently large. So what would be the sign of the whole thing? If this is sufficiently small, it will be positive, because this one will be much less than this one. So gravity will overcome, will win, right? And if k is sufficiently large means the wavelength of the disturbances is sufficiently small, which means in the small k case, we have long waves. In the sufficiently large case, we have short waves. So the short waves will make this guy negative, which means that this state h equal to h0 will be stable. Okay, so short waves will be killed by whom? By surface tension. This guy is very strong on the weak guys. Okay, the short waves it kills immediately. However, for long wave disturbance, okay, the surface tension is very weak, because the effect is the capillary effect is proportional to the second derivative of the interfacial shape. Okay, so if the wave is very long, okay, so the second derivative is next to 0, not 0, but not large, not excitingly large. So it will be a positive. So the resolution of this is shown here. Okay, so the growth rate is actually a positive if k squared is smaller than this value, and this is called bond number. Now the bond number, this is the ratio between the gravity effect or the body force effect and the capillary effect. Okay, this is the bond number. So okay, so okay, so this is the graph showing the growth rate as the function of the wave number, okay? If for sufficiently small k, it's a positive, which means the system is unstable, linearly unstable, and then it decays for sufficiently large k. From here and on, it becomes a negative, which means the short wave disturbances are stabilized, the long waves are destabilized. So that's why this guy, okay, will not remain forever, okay, even for 1 centimeter thickness, even for 1 millimeter thickness, it will not remain there. It will become unstable towards, with respect to sufficiently long disturbances. Okay, it reminds me the following thing. I don't remember which stage of my scientific career. I think it was somewhere between the 5th grade and maybe the 7th grade, or maybe a little further. I remember the physics teacher. Well, I hated her, but for no reason, actually. She showed the following experiment. I don't remember she explained it. So I thought about this experiment for many years, and now I know the answer. Okay? So the experiment was like this. So she brought a bath, a sufficiently large bath, okay, empty bath. I put water there. And then, okay, she overturned this. So the system became exactly like this, right? Okay, water is here, and G is here. So guess what happened? A little rain, right? Okay, you are right. Now, the next experiment adjacent to this was the following. She brought a piece of paper, but not a paper, but sort of rigid paper. And then she covered this guy with the paper. Actually, she filled all of this bath with water, and then she put this rigid paper on top of it. And then she overturned it again. Guess what happened? Same thing. Nothing happened. And nothing new happened. And then there was experiment number 3. She brought a little beaker and filled it with water up to here. And then she put the same paper, or similar, I would say, not the same because the same fell down. It was already wet. Okay? And then she did this. She overturned it. Guess what happened? And what happened? Nothing happened. It remained like this. And then she asked why. Nobody knew. Okay? So I'm asking you what happened. Why? It took me, believe me, several years to understand. Several means more than 10. Okay? It's not like many, it's more than one. No, several, it's more than 10. Okay? To understand why. Actually, here is the answer. Okay, here is the answer. Now, if you have this system, which we understood that it cannot survive like this, right? We understood this quite well. Now we ask, so the system like this, system of infinite extent, it cannot survive. Now the system becomes of limited extent, all right? It's not infinite in this direction, it's limited now, okay? Now we do this experiment, okay? So what kind of wave number we allow for this system to disturb the system? Somewhere here, because the system is large. The wave number is 2 pi divided by the length, right? If the length is sufficiently large, so the wave number is sufficiently small, so we are somewhere here. If we are somewhere here, so the system becomes linearly unstable, or wants to be linearly unstable, so it goes down. That's exactly what happens with this guy. Okay? However, if we look now at this little beaker, the length is very small. I don't know. something like 1 centimeter in diameter or something like this. Okay, so if L is sufficiently small, so K, the wave number is e2 pi over L, is sufficiently large, right? So we are apparently somewhere here, and the system wants to be stable. So that's exactly what happens. So in this case, when we are stable in this sense, what happens? That's exactly this kind of a calculation. In this beaker, you probably you put 10 meters, so after 10 meters, apparently it will stay like this, right? So it means if you bring sufficiently skilled, repairman, and you ask it to cover the whole ceiling like this with 10 meters of water, and if they work, I don't know, 24 hours a day, and they put it very well, so it will stay. But the problem is that one little disturbance somewhere, it will bring it down. Okay, so this is the lesson we learn from here. Okay, so this is, Rayleigh-Taylor instability. Now, seriously speaking, this is the case when you have a heavier fluid, on top of the lighter one. That's exactly what happens. You have a water above, I don't know, air, or above some lighter fluid than water. Okay, so that's exactly the case. That's exactly the case of Rayleigh-Taylor instability. So just maybe a little bit generalizing this observation, what we are saying, the Rayleigh-Taylor instability is actually the case where the heavier fluid accelerates into the lighter one. Okay? It may be like this, or it may be like explosion. Think about you have a heavier liquid as a sort of something like this here. You have a liquid here, you have some other liquid here, and you explode this guy. So there is a wave going in that direction. So actually, so to speak, this heavier liquid accelerates into the lighter one. It will be similar effect. It will be different because of geometry. It will be different because G is acting in different direction. But G is just a mechanism showing you the direction of this acceleration. So you have an acceleration in this direction, you will have a similar effect. Okay, but what happens with time? It goes continuously in one direction, right? Today, somehow. Okay, let me maybe just a few moments, I think 3 more slides, and then we'll take a break, because I feel now my throat is exponentially deteriorating. Okay, so, again, I would like to understand from the mathematical point of view what happens with this system based on the same consideration as we did before. Okay, so the equation is basically the same. Okay, remember the nonlinear diffusion term just changed its sign. So the manifestation of this is exactly here. In the previous case, we had GH squared. Now we have minus GH squared. Okay, so this is F. I don't know whether it's a free energy of this system or not. I don't know whether it's Lyapunov functional or not. I want to see what happens with this guy. Okay, so again, differentiation. Believe me, it's the same thing. The only difference is this negative sign in front of G. So we have minus here, we have minus here, we have minus here, and here, and here. It becomes already boring, and here. Okay, so now df by dt it is equal to this guy. How about his sign? And the hint is here. Don't look at it. It's negative, right? So which means this functional of h, it goes down, it decreases along any trajectory, because this is not linear stability analysis. This is sort of global consideration of this mathematical object, which is the evolution equation. Okay, it starts from some initial disturbance. It goes somewhere. I don't know how. I don't know where. But the only thing I know, df by dt, this value decreases with time. Okay. And what was the other ingredient we spoke about? So to have this guy to be called a free energy of the system, we have to decrease it with time, right? And we want to be bounded from below. And then we'll be sure that there is steady state for this system. Okay. How about boundedness from below when we look at this guy? Is it bounded from below like in the previous case? What do you think? If it's a positive sign here, so then definitely it's larger or equal to 0. No doubt about this. How about this negative? Well, it's complicated. And it's complicated only because it's not bounded from below. It can be shown, but it's not easy, but numerically you see it. It's not bounded from below. Because you can make this h larger, and in some location you can make it larger and larger, so this will be the main contribution, so the whole thing will be actually more and more negative. Okay, so it's not bounded from below, which means that nobody promised us, okay, like in Israel we say, nobody promised you a rose garden, so nobody promised you a steady state here, okay? Well, everything can happen. And in fact, there is no steady state. There is no steady state, actually it doesn't exist. And it can be shown numerically. I will show you. Okay, and basically what happens, yeah, I should be cautious. Non-ruptured steady states do not exist. Non-ruptured means the local thickness of the film, I mean, if it's somewhere at some time becomes 0, so it means that the film is ruptured. If this is the solid, so the film looks like this, and here it's 0, so it's ruptured. It's not continuous anymore. It touches, so we have a contact between the three phases, between the liquid, the solid, and the gas outside. Okay, this is rupture. So non-ruptured, which means everywhere in the domain, the local thickness is non-zero, is positive. It means non-ruptured, so non-ruptured steady states do not exist. Okay, how about ruptured steady states? Well, okay, here is last night. Okay, I wrote this. Look at this equation. Now let's write. Okay, that's our equation, right? Okay, let's write it in this form. It's exactly the same. Now look at this guy. If you bring it to 0, so then the whole thing is 0, right? Okay, so it's very easy to solve this. Okay, ordinary differential equation, second order. It's a pleasure to be solved, right? So this is one of the solutions. Okay, one, because you have to start with one, that's the mean thickness of the film, right? Okay, so if you substitute this guy, phi is just a phase, a constant. Okay, you substitute it here, and you find this is 0, and this is time independent, so it's 0. So which means that, what does it mean? It means the following. You can arrange, okay, this is your substrate. You can arrange some sinusoidal waves, something like this, up to here, up to 0, right? And then you can, somewhere else, you can put another sign. You can fill your domain up to infinity, plus infinity, and minus infinity with these signs, or cosines. It depends on the phi. And that's it. It will be a steady state because it satisfies the equation, but it's ruptured. I mean, well, by the way, I don't know. I think it will not stay if you try to solve this equation numerically. Definitely, it will happen. Something I believe somewhere. I mean, numerically, somewhere where the local thickness was 0, it will become negative, and the whole thing will blow up. Your numerics will collapse. Okay, so it will. So I don't know. It's meaningless to ask whether this steady state is stable or not, because it will be meaningless. But anyway, if you are stubborn enough and ask me whether there are steady states, maybe ruptured, so this is one of them. And maybe the last slide before the break. So if you try to solve this numerically, so this is our equation. Okay, look at this. This is the ceiling, so G is acting in the negative direction, right? Okay, this is the ceiling. So you start with some initial condition. After some time, you see something like this. What is this? Like a stalactite from the ceiling, right? So this is one of them, this is another one, and here it looks like it goes like this. It goes something like this. So somewhere it touches 0, and that's the end of the story, because you cannot continue anymore. This is the end of your evolution of the system. That's the end of your numerical solution, because you cannot continue anymore, because in your model there is no contact between the solid surface and the liquid, and the gas. Okay, so the liquid was continuous, now it is continuous here. So if you want to continue, you must bring in new physics into your mathematical model just to allow it to continue from this place and on. Okay, if you don't do it, so this is the end of the story. Okay, there is a rupture. Okay, the film ruptured. It displays now a few stalactites. Well, in this case, one small, one big, and that's it. Okay, so basically, the film, okay, this film, which we arranged, put it very carefully 7 meters thick on the ceiling, and we did not breathe because we did not want to disturb it, but it fell down, but it didn't fall down like this, like a solid surface. It will fall down something like this. So it will arrange for some locations, and these locations will have some stalactites, some like this, and there will be some depressions which will be closer to the ceiling, and there will be liquid going from here. Okay, imagine the ceiling is not here, but here. What happens? This guy wants to be bigger. This one wants to be bigger. So these big fat guys, they live on the expense of whom? Of this little guy in between. So they suck the liquid from here to here and to here. The rich guy becomes richer, and the poor guy becomes poorer until it breaks. Okay, fine. And this is exactly what I said. At some stage, at some time, at some location, there is rupture, and that's the end of the story. Okay, so I will leave you, well, let me skip this. Okay, I will leave you with this title, and we'll start discussing this maybe after break. Okay? So 5 minutes break. Is that okay? Okay. Okay, good. Substrate, you can do it in an oblique direction, which is a combination of this and that. Or you can do something else. You can use not temporal forcing like this, but spatial forcing, putting this guy on a corrugated surface and doing something, and maybe combining this spatial forcing due to corrugation of the substrate and a temporal forcing just by shaking it. So all kinds of combination, it can be present here. So, but before we discuss this, I would like to skip this part, and I would like to, especially due to the fact that I have only 20 minutes or so, we can negotiate 5 minutes more, 5 minutes less, but it will be the same order of magnitude, right? Okay, so I would like to think about what kind of forcing of a physical system, especially of a fluid system, what it can do for us. Well, before I do this, let's consider, that's exactly this, okay? Let's consider a pendulum. Okay, that's, I think, the first mechanical system we ever experienced in our lives, right? Beginning maybe at epsilon squared age, something like this. So you know, this system is really fascinating in the gravity field. If the gravity field is like this, and we have a pendulum, okay, so we know actually almost everything about this system. Okay, for example, we know that this system has two equilibria. Okay, one equilibrium is when this guy is pointing downwards, and the other equilibrium is when this guy is pointing upward. Okay, and we know that the previous, actually the former is linearly stable. So if we disturb the system around it, if it's pointing downwards, so it will come back in the gravity field, right? And if we disturb the equilibrium, which is pointing upward, what happens? It will fall down. It will never come back unless you push it there. Okay, by itself, it will never come back. If it's something like this, you disturb it, so it does like this. It goes towards the other equilibrium. Okay. Now, what happens if we apply sort of forcing to the upward directed pendulum? Okay, and this brings us to this famous example, which is called inverted pendulum, or sometimes it's actually called Kapitsa pendulum, but it's not really, it doesn't make justice to Stevenson, who discovered this in 1908, and the Kapitsa did it somewhere in the 40s, some 3 decades later. But anyway, it's called inverted pendulum, and the following is about it. So now let's assume that we have the same pendulum, gravity is directed in downward, here, in yellow color. And now we put the base of this pendulum in some channel, and this channel is a vertical one. And now we are allowed to shake the base of the pendulum up and down with a certain frequency, omega, a certain amplitude. Okay, now it turns out that this new system, at least in the limit of small amplitude and large frequency, this new system has 4 equilibria. So it acquires 2 new equilibria. And now the question is, how about their stability? It turns out that the 2 new equilibria are linearly unstable, so just fake, a mathematical fake maybe, because the nature never heard about these new equilibria. Now, the equilibrium pointing downwards, which used to be stable, it remains stable. This does not break its stability. However, the upward position, which used to be linearly unstable, now it becomes stable, provided that the product of the frequency and the amplitude of this forcing, okay, exceeds a certain critical value. Okay, so you can experience it. Take a broom with a long stick, you put it on your hand, and make the brush pointing upward. And then, of course, if you wait like this, so this guy wants it to fall down. Okay, so how to stabilize it? You do it something like this, right? And then it stabilizes. That's exactly the thing. Oh, similar. Okay, very similar to this. Okay, there is also one more example of this Kapitsa pendulum, which is called a Chalamet pendulum. It's much younger. It's 1983. And actually, by now, nobody actually, even these guys, they wrote a paper in 2001, and they argued about something, about some explanation made by some other guys. It's still very much unclear what's going on. Okay, so what's the system? The system is the following. Imagine you have this guy. You have a Kapitsa pendulum, okay, inverted pendulum, and then you put a slider on the stick of this pendulum. Okay. Now the slider it has some friction between itself and the stick of this pendulum. So if you put it like this, so it will go down. Okay. So now you try to stabilize this one. Imagine here is a slider, like here, okay? So you oscillate the whole thing in the gravity field, up and down, up and down, up and down, with a certain frequency, certain amplitude. And it turns out that this guy it will not go down. It will find some location along this stick, and it will stay there. Stay there doesn't mean it will be stuck there. No, it will oscillate somewhere around certain location. And it will not fall down. It will not go up. Okay, so it will find a location. It will stay there. Will oscillate around that. Okay, so and actually I never saw a reasonable explanation what happens with this guy, and even this paper did not clarify anything for me. So if you are aware of any paper about this, please let me know, because it's really kind of intriguing. So I don't know the answer. Well, sometimes it happens. Okay, anyway. Okay, so now, after we saw these kind of examples for a simple mechanical system, now let's look at less simple mechanical system, which is a fluid system, liquid system, either film or drop. Okay, so for example, here, let's look at the situation when we have an inclined plane. Okay, alpha, this is the inclination angle. Okay, a gravity field pointing this way. You put a drop here on the incline, and now you start oscillating this guy up and down with a certain frequency, certain amplitude. Now, these guys, now immediately I will reveal the identity of them and I will show you the results. So what they did, they used very large domain for the volume of the droplet. Well, not very large volume, but sufficiently wide range, okay, in microliters. Okay, so the angles were up to 85 degrees, so which means almost vertical, right? Okay, and then this is the value, the range of the frequencies they used between 30 hertz and 200 hertz. Different liquids with different kinematic viscosity. Okay, surface tension was around the same value. And the acceleration imparted by this shaking, it was up to 50 G. Okay? And the contact angles were in this range, about 77 degrees here and 44 degrees there. Okay? A plus or minus. Okay, so what they did, they looked at this system and at its response to this shaking. Now I would like to ask you, what would you think, okay, happens? What are the possible scenarios if you don't shake it? You put the drop here, go aside and look at it. So what can happen? Okay, real life experiment. So no expectations? Okay, what do you think? Okay, it may go down. Well, that's definitely a possible scenario. Is there any other possible scenario? It stays, yeah, sure. Okay, so now we understand that it can either stay in the place, okay, held by what? By viscous friction. So the gravity force in this direction is not big enough to move it downhill. Or it may, or if the gravity force is sufficiently large, so it will slide down, nobody will stop it. Okay, fine. So now let's look here. So these are the guides. This is a paper, a physical review letters in 2007. Okay, Brunet, I don't remember the second one. The third one was Eggers, Jens Eggers. In Bristol University, this guy, Philippe Brunet, now he is in Lille University in France. Anyway, that's what they found. Now look at this plane spanned by the frequency and the amplitude, actually acceleration, but it has to do with the amplitude of this forcing. They found 3 scenarios. One, that's exactly what you said, is over here. One is over here, static, doesn't do anything. But look here, there is another one. They climb. They can climb, not only slide down or stay in place. They can climb up, okay, uphill because of this. Okay, so there is some theoretical work by Uwe Itile and Karen John, Karen John also published a few years ago. Well, it gives some explanation for this. Okay, so Okay, so basically, it would be interesting to see when we go along one of these lines, like this one, it corresponds to, well, to a certain frequency. So now we are going from zero amplitude means, zero acceleration, which means zero amplitude, will go from zero amplitude, will increase it and see what happens. Okay, so as we see here from this phase diagram, so we see first for sufficiently small accelerations, it will stay, and then it will go down, and then it will stay again, and then it will climb up. Okay, so let's see what happens. Okay, so if we are, what happens? Okay, if we are here, okay, so it will stay. Now we raise the acceleration a little bit up, so now the drop slides down, so that's how it looks like. This is, okay, that's a front edge, and this is the trailing edge. Now, if it's static somewhere here, so it looks something like this. Stays like this, doesn't know what to do, so it stays in one place. But if we are here, so it looks something like this. It goes up. So this is the trailing edge, and this is the front edge, so it goes up. Okay, so that's a morphology of the droplet moving up. But it turns out that there are several scenarios for the drop to go up. It can go up like this. It can go up like this. What's the difference? Look here. The tail develops some spike there. So there is, okay, an extra tail, okay, which is sort of narrow and more pointing here. Or it can be like this. Okay, what's the difference between this and this? Maybe the picture is not good. This guy disintegrates into little droplets, okay, because of a capillary instability. So it's like a liquid cylinder breaks due to a capillary pressure. It breaks up into droplets. So once it becomes sufficiently elongated, so it will break up into several droplets. Okay, so it's kind of intriguing effect. Okay, what can we look more here? For example, if we look at the capillary number, so this is the cousin of our inverse capillary number, which we used in the previous part. So the capillary number is shown here. It's mu times u, the typical velocity, divided by the capillary by a surface tension. So which means that if surface tension is fixed and mu is fixed, so u, the faster is u, so the faster is the larger is the capillary number. Okay, so what happens if, by the way, if u is a positive, so the capillary number is a positive. If u is 0, so the capillary number is 0. If u is negative, it's the same will happen to the capillary number. And just for scaling, the capillary number of 1 over 1,000 means u is about 1.8 of millimeter per second. So it's a sizable velocity. It's not supersonic, but it's sufficiently discernible. Okay, so look here. Okay, this is the acceleration. So for small acceleration, we are here. Look at the capillary number. It's 0, more or less, right? So it's going to be 0 up to, I don't know which value, somewhere here. So it goes like this. Now this is the blow up of this region. It's 0, and then it goes down. What does it mean it goes down? It goes down, it means we are here, right? It goes down, it slides down, but then it doesn't want to slide down anymore. It goes up. It becomes less negative, so we are here, and finally it reaches this destination where the capillary number is 0, so it stopped again, okay? And then what happens? And then we are here about, I don't know, 0.7. How about 0.7? Yeah, somewhere here. And then it goes up, okay? So that's exactly what we see there. Okay, now let's look at a different projection. This is the position of the upper contact angle, and this is the position of the lower contact angle, which means this guy doesn't, if it climbs uphill, it doesn't go monotonically. No, it oscillates. It goes a few steps up, a few steps down, but the number of steps it does uphill, it's bigger, larger than the number of steps going down. So it's non-monotonic, but you see the inclination, definitely it moves up. Okay, and by the way, this is the lower contact angle, the same. The same, it goes non-monotonically, you see the inclination, but it goes non-monotonically, it oscillates, but going uphill. Fine, okay, let's look at another example. This example was published also in PRL 2 years after that. Noblin, Kaufman, and Celestini from France and some university near Marseille, by the way. Sorry, Nice, in that area. So what happens over here? What's the difference? They have a drop on the horizontal table, but now the horizontal table is connected to two shakers. One shaker and the other one. This one, it knows only one thing to oscillate left-right in the horizontal direction. This one is vertical shaker, so it knows only one thing, it oscillates up and down. Okay? And both are independent, so you can tune different amplitudes, different frequencies, which means actually, if you think about this, this means that the acceleration imparted on this drop, a poor drop on the table, okay, it may be oblique. So by changing the accelerations of the horizontal one and the vertical one, you change the direction of the acceleration imparted on this drop. Okay, so what happens here? Okay, here is one of the results. Look at this drop. So by the way, this is the reflection. So I added this blue line, that's the location of the base, of the substrate. The rest, what you see underneath, is just a reflection of the drop above. Okay, what happens here? This is the beginning of the story. This one, what do you think? It wants to move? Or it wants to stay? This one. Just by looking at its configuration. It wants to move. In which direction? Exactly, to the right, because the gradient here is more than there. So it wants to move in the direction of the larger gradient. You are right? Okay. Sometime later, a 1/10 of the second, it looks like this. It wants to move. It wants to move. In which direction? It's still here. Okay? But now, this time, it moves, but in this direction, because now the front edge is here, and it wants to move over there. How about here? It wants to move in that direction. Okay? So, you see, you can play with this guy, sending him left, right. Okay, basically, if you look at the position of the right contact line, which is here, you see what it does. Okay, it makes some oscillations, but is there any tendency here? Definitely, it wants to move in that direction. It wants to increase the sort of average value of the location, so which means it wants to move to the right. Okay. Okay, fine. Okay, another, yeah, and actually this is a puzzling example. Okay, another puzzling case. Well, that's from my lab. We published the paper in 2007. Then we didn't know the explanation of the effect. And if you ask me now if I know, no, the answer is not. I don't know why what we saw is happening. Okay, so what happened? Oh, by the way, what happens with time? 5 minutes or? Let's negotiate 6. 5. Okay. So I will finish with this and say goodbye. Okay. Not for a long time, for tomorrow. Okay, actually, okay. This is the physical system which we have. Okay, we have a vertical cylinder, vertical rod of about 50 centimeters long, 50, half a meter. Okay, and here we have a reservoir of the liquid, and the liquid was a glycerol. It was, I think, it was 94% of glycerin and 6% of water by weight. Okay, so the viscosity was very large. Okay, so okay, we poured this liquid on this vertical cylinder, and we watched what happens. Now, there was one more ingredient in this system. We had this ultrasound horn attached to the system. Okay, so the effect was to excite vertical vibrations of the system. Okay, actually, the deficiency of this system was the following, or maybe its advantage. I don't know yet. So the frequency was fixed. The frequency was 20 kilohertz. But the maximal amplitude of this vibration was 125 microns. And we didn't know about this limitation long in advance. So what was the outcome of our experiments? You can imagine. We burned out this thing because we tried to exceed this value for sufficiently long time. And then we had to pay $20 to repair it, and we said, forget about it. Okay, so we tried to excite it. Okay, so these are the three examples of configurations we got. This is the case where A was 0, the amplitude of a vibration was 0, which means just standing static cylinder with liquid running down, and we look what happens. So what happened? This is what happens. There were droplets, by the way, asymmetric, and this asymmetry was, axial asymmetry was apparently associated with viscosity. So for less viscous liquids, the configuration it tended to be more axisymmetric. Okay, so it was something like this. So we measured the spacing between the droplets, and we measured the speed of the droplets. They surprisingly fit very well with the standard axisymmetric calculation for the speed of the drop and the wavelength of the pattern you expect from linear stability theory. They were a few percent away, but not more than a few percent away, which we said, okay, sufficiently good. Okay, so now we started oscillating this guy. Okay, now what you see here, this is far away from the edges. It's far away from here, far away from here. So the whole system was about a half a meter long. So we looked only at the middle third of it. Okay, so it was about 16 centimeters from here, 16 centimeters from here, and the scale, this is 1 centimeter. So you see many guys like these are in the middle third. Okay, so what happened? When we raised the amplitude of a vibration from 0 to 75 microns, this is what we saw. Okay, we saw, when you look at the configuration is very much different. So it's not like a droplet-like structure, but it's sort of something more diffuse. There are no distinct objects like droplets. So the first thing we saw is that the surface was not moving. It was not like here when these guys were running down. Okay, so the surface did not move. Okay, and then we said, how come? What happens? And then we looked here, but this guy was not transparent. So we replaced it with a transparent reservoir walls, and it put some marks on it. Okay, so what we saw in this case, so the liquid level did not go down like here, like in this case. It did not go down. It was oscillating, which means we succeeded to negate gravity, so to speak. Okay, so the flow just stopped. It was arrested. Okay, so when we raised the amplitude from 75 to 100 microns, so we saw something like this. This is different from this guy, and this is different from that guy. It's more a droplet-like again, but again it was not moving. So the droplets were static. There was some movement here, but not in the middle third. Okay, so there was some dynamics in the upper part. There were some other effects, but I will skip them. So we don't know what's the reason. I know at least one of the reasons why our subsequent theoretical modeling did not work for this case, because actually we looked at the base state to be a Nusselt flow. But when you look at this system and you calculate Stokes viscous layer thickness, then you find that it's about, for very large viscosity, it's about 2 centimeters for this case. But the mean thickness of this guy was barely 1/4 of a millimeter. So which means that definitely Nusselt flow is not there. It's something else. But by now we don't have a good theoretical model to model this and to explain the thing. Okay, I think I will leave you on this happy note. So think about this. Maybe you find an explanation. Tomorrow we are meeting at the same time, same place. Maybe someone brings the explanation for this paradox. The last sentence before we say goodbye for a few hours is the following, that there are so many paradoxical results which all of them stem from a laboratory, from experiments. So there is a strong drive nowadays to find explanations for all of these effects, and or maybe to look at some standard film, liquid film, or drop, or both configurations under external forcing, and to see what would be a response of these systems. Now, I will show you tomorrow, I will continue with this, I will show you a few movies we made, okay, from some experiments similar to that, and then we'll start the theoretical part, at least to try to mimic these results. There is no comparison between them. We cannot directly compare, but we see some tendency which is certainly indicated that we are in the right direction with respect to the experiments, but we are not still there. Okay, thank you very much for your attention, and see you tomorrow at the same time, same place.